This video contains how to do several different things, but they're all very closely related, so we'll try to cover them a little bit quickly. The first thing that we're going to learn how to do is how to evaluate a one-sided limit. We've already talked a little bit about this in our limits discussion, but this is a little bit more official. How to do continuity at a point, and then continuity on an open interval. This is open versus a closed interval. And then we're going to talk about what is called the intermediate value theorem. So those are our main objectives for this video. The first thing we're going to talk about is a one-sided limit. So this begs the question, what is a one-sided limit and what does it look like? There are two types of one-sided limits. There are limits from the left, like that, and there are limits from the right. And these limits look very similar to the other limits that we had, and that's okay because they're both limits. Great. The only difference is, notice, there's a minus sign above the C, or a plus sign above the C. That's the only difference between a regular limit and a one-sided limit. And so a left-sided limit, you're approaching C from the negative side of C, from the left, and a right-sided limit, you're approaching C from the right side or the positive side of C. Here's an example using a chart. I'm just going to use the same example we had in that first video with x and then the function y equals x squared. And so I'm going to draw up the same exact chart. You don't have to copy this down. Maybe flip back to your notes. I'm going to copy down the answers really quickly here. When we did this before, we essentially did two limits. The first limit was, notice in blue, we are approaching 2. And the blue numbers 1.9, 1.999, etc. are approaching 2 from the negative side, from the left. So this is that left side limit, and we can see that the left side numbers here, the y values, these are all approaching 4, like we suspected. So we can say that the limit as x approaches 2 from the left of x squared is 4. Okay, we know that from before. And similarly, the green, okay, if we approach from the right, 2.1, etc., then these numbers are also approaching 4. And so we can say that the limit as x approaches 2 from the right, that's the positive, of x squared equals 4. The big note here is that notice that these two limits are the same. So the big idea here, note, is that the limit as x approaches 2 of x squared equals 4, and that's only true, this limit, the limit in general, can only exist if both the left and the right hand limits are the same number. Here's a special function that demonstrates that you can have two-sided limits that come to that don't have a limit in general. So here's a function that goes along here at -1, stops at 5, jumps up to +1, and then keeps going. Alright, and so we're going to do this graphically. The limit as x approaches 5 from the left of f of x, well, if we look at it, we're following those y values, and those y values are staying at -1. So the left-hand limit is simply -1. And then for the limit from the right, we do limit x approaches 5 from the plus side of f of x. And this limit, well, we're approaching 5 from the right, and those y values are staying at 1, so that limit is 1. Notice here that 1 and -1 are not the same, therefore the limit in general, as x approaches 5, no plus or minus, of f of x does not exist. That's the big idea to get from a one-sided limit. Just to reiterate one more time, let's say that you're given that the limit as x approaches c, some number, of some function equals L, some other number. In your head, you should think right away that this means that the limit as x approaches c from the left of f of x and the limit as x approaches c from the right of f of x, both of these limits must be L. They cannot be anything other than L. And similarly, if you're given that this limit is L and also this limit is L, then this works the other way. That if these two limits, the two one-sided limits are the same, then the limit in general is also that same number. Here's a picture. I like pictures. Check it out. We're approaching the x value of c. Here it is. And the y value that we're approaching is L. Here it is. So there's some point. Maybe it's a point. Maybe it's a hole. I'll draw it as a hole. Maybe there's some hole that we're approaching from the left and the right. But notice that the function is always going. Oh, that's not a function there. Ooh. The function is always going towards the hole, and it could look like anything really. But notice that, essentially, for the limit in general to exist, the limit from the left and the limit from the right must be the same. Next thing we're going to talk about is continuity. What do we need for continuity at a point? That's a question mark there. Well, the first answer, we need two things. The first thing is we need a point. In order to be continuous at a point, you need to have a point. What's the point? It's math. Love it. Let's say that we have a point. We'll give the x value a value of c, and we'll give the f of c value, we'll call this L, just for c and L for limit. We're getting there. So here's a graph of what's going on. We have our x value at c. There it is. This looks very similar to the last picture. Here's L. All right, and we need a point, not a hole, a point. There it is. Look at that. Great. And now what we need is we need to have the function go through this point. Okay, it can't just sort of jump from a hole up to the point. It's got to go through it, both from the left and from the right, in whatever way it does, but as long as it goes through the hole, we're fine. And so the way that we mathematically do this is we say that the limit as x approaches c from the left of f of x, this has to be the same. Okay, as we go along here, it's got to be the same as the limit coming in from the right. So we should be able to see that and convince ourselves that that is true, that the limit from the left has to be equal to the limit from the right, and one more condition. Right? If it was just these two conditions, you could have a situation where the function's down here, comes to a hole, goes away. Right? These two conditions are satisfied. But this is not satisfying our continuity, because there's a hole here and that would jump up and come back down. In order for this to be continuous, the last thing is that these two one-sided limits must also be equal to the value of the point. You could think of it as, well, we have some point up here and we're dropping it down to be wherever this limit is. So that's what we need for continuity at a point. We need a point where f of c equals L, and we need the two limits to be equal to L as well. Continuity with functions is pretty intuitive when you think about it. So if we have continuity on a closed interval AB, that means that we have some two x values a and b, and because they're closed, that means that they are part of the function. Okay, so closed interval, that means that you have some point at a and some point at b, and if the function is continuous, that means that you can draw any function without lifting up your marker, your pen or pencil, or your electronic iPad stylus. And as long as you connect a and b, and here are the y values f of a and f of b, you're good to go. This function is continuous. Okay, maybe I broke some rules here. Pretend that has like a negative slope and not like an infinite slope. But yeah, you get the idea that for continuity on a closed interval has to have endpoints, is the big idea here. Versus continuous on an open interval. And for an open interval, you can have two things that don't have endpoints. And the first is that you could have a vertical asymptote, and the second is a hole. So you could have any combination of asymptote, asymptote, hole, asymptote, etc. And now the function could do something strange, like go up to positive infinity, and then sort of wobble around, and then come to this hole. But notice that a and b are not in the domain of this function, because a is an asymptote and b is a hole, and so f of a and f of b are not defined. Alright, so that's how you can get continuity on an open interval, is basically whenever you have an asymptote or a hole. Last thing is called the intermediate value theorem, or IVT. It basically says this: if f is continuous on the closed interval from a to b, then f hits all y values between f of a and f of b. The IVT is very intuitive again. Basically, you have a graph. Here's A, here's B. Notice that f is continuous on a closed interval, so that means that there is some point at A and some point at B. And if we plug in A, we get f of A. If we plug in B, the y value is f of B. And now, the idea with the IVT is that you, in order to connect A and B with a continuous function, you must hit every single value between A and B. So any way we draw it, we'll always hit every single value. Notice that it could go up first and that it could go down below f of b, but it always hits every single value between them. That's the IVT. Pretty intuitive, not used that much.